All right, so now that we've derived the product rule or established the product rule and quotient rule in our understanding for finding derivatives, let's find a derivative of a trig function. So I'm going to look for the derivative, the d dx, I've just written it in a different form, of cotangent of x. Well, at first, cotangent of x seems like it would be too difficult to figure out because what would I do with this? But let's remember that cotangent of x is really exactly the same as cosine of x over sine x. Now all I have is a ratio, so I can use the quotient rule, and I know I'm going to need to find the derivative of the top and the derivative of the bottom at some point. So let's remind ourselves that the derivative of cos x equals negative sine x. We learned this with the squeezing rule. And that the derivative of sine x is positive cos x. All right, so now let's go ahead and find our derivative. We want the derivative of the top times the bottom as is, minus, and I'm going to protect my negative, the derivative of the bottom, sine x is cos x, times the top as is, all over the bottom squared. Okay, let's do a little simplifying. Well, I have negative sine squared of x minus, and now I can remove the brackets, minus the cos squared of x all over sine squared x. Simplify farther, if I pull out a negative, then I have sine squared x plus cos squared x in the numerator over sine squared x, which is just negative 1 using a trig identity over sine squared x. But this is really just negative cosecant squared of x. So I can say that the derivative of cotangent x equals, and I should say up here, this was badly written now that I'm looking at it, that the derivative of cotangent of x equals the derivative of cosine x over sine x, and the derivative equals opposite cosecant squared of x. So we've just shown one derivative for a trig function. The truth is, trig functions are just like when we worked with learning these two. They needed to be committed to memory, and they need to be committed to absolute instantaneous memory like your math facts were in elementary school. So no playing around with, oh, I can figure it out when the time comes. These need to be committed to memory as soon as possible. So we have the derivatives of sine and cosine. Let's work on the other four. Let's develop the other four derivatives. I've proven one, so we know that the derivative of, well, where can I put these? Let's put them all together. So I have the derivative of cosine, negative sine, the derivative of sine, cos x, the derivative of cotangent we just showed is negative cosecant squared of x. The derivative of tangent is shown in your textbook, if you want to see the proof or the derivation like we just did, is secant squared of x. And then the other two that I haven't shown, but I'm sure you can find them on the internet if you want to know, are the derivative of secant x. And you might even be able to derive it yourself because you would just use the same rules I used. Turn secant x into probably 1 over cosine x, and then use the quotient rule. So secant x is secant x tan x. And the derivative of cosecant x is negative cosecant x cotangent x. So these need to be committed to memory as soon as possible. All right, so let's do another example. And I'm going to show these because now that I have moved on, I realize that I need to make a point about differentiating trig functions. If you, unlike algebraic functions, which tend to always come out with the same looking answer, trig functions can be written in different forms, as you know from working with trig identities. So when you find the derivative of a trig function, sometimes your answer won't mesh with your neighbor's answer or perhaps the answer in the back of the book. So let's look at an example where that's the case. Suppose you want to find the derivative of the function y equals 1 minus cos x over sine x. So we go ahead and we take the derivative, and I'm going to come over here and I'm going to take the p of x, or the p prime of 1 minus cos x first. So to find the derivative of 1 minus cos x, well, 1 is 0, so I have negative, and we know that the cosine of x is negative sine x, so that equals sine x. The q prime of sine x equals cosine x. Okay, so to find the y prime, I would look for the derivative of the top, sine x, times the bottom as is, sine x, minus, protecting that negative, the derivative of the bottom, cos x, times the top as is, all over the bottom squared. All right, so if I simplify, I get sine squared x in the numerator minus, still protecting that negative, cos of x minus cos squared of x, all over sine squared x. Now I can distribute the negative. I get excuse me, sine squared x minus, and I'm going to rearrange these two, so I want plus cos squared x minus cos x over sine squared x. I recognize that this just equals 1, and so separating across the negative, separating my fractions or my denominator into different numerators, I get 1 over sine squared x minus cos x over sine squared x. And now that I've done that, I realize I think that's not necessarily the prettiest way to do it. So I'm going to make 1 minus cos x. I'm just going to put that back together in the numerator over sine squared x. Just looks neater. They're both good. But notice already, this is one form. Your neighbor could have given this answer on a test and it would have been 100% correct, or perhaps you calculated to this answer and this answer is the form on the test or the form that you need for another application later. You need to be able to recognize between trig differences, or the identities for trig identities. You need to be able to recognize conversions from one to the other. And let me expand on that by showing you another way to calculate this same derivative. So if I have y equals 1 minus cos x over sine x, perhaps your neighbor immediately went, well, that just seems kind of crazy. I'm going to convert this to 1 over sine x minus cos x over sine x, but that's just cosecant x minus cos over sine is cotan x. And that is super easy to find the derivative of. The y prime of this function is just whatever the derivative of cosecant is, which we have, right? here, right? Negative cosecant cotan minus whatever the derivative of cotan is, which we only a moment ago derived as opposite, or change the sign, opposite of cosecant squared of x. Now I have a totally different looking answer. It would look like you and your neighbor got completely different answers, but in fact you did not. And to show that, I'll work backward. So we have negative, well, cosecant is 1 over sine x times cotan is cosine over sine x plus cosecant x would be 1 over sine squared of x. So I have negative cos x over sine squared x plus 1 over sine squared x. I have the same denominator, so all I'm going to do is put them together, and I'm going to reverse so that I get the 1 minus cos x, 1 minus cos x in the numerator over sine squared of x. I clearly have exactly the same answer as my neighbor. So we have the product rule, the quotient rule, and now we have derivatives of trig functions. Last thing we want to do before we move out of this section is look at higher order derivatives. All right, so I'm going to use the position function to do that. So we have the height of an object at a given time is equal to negative 16, and this is in meters per second, t squared plus the initial velocity times t plus the initial height. All right, so this would be the position of an object falling under the force of gravity. How high is it from the ground at any given time? So if this is the ground, what position is it after some given t? And if the object is dropped and only under the force of gravity, then initial velocity would equal 0 because it was only dropped. This would come out, and the only thing that would affect how high it is from the ground would be its initial height from the ground and the force of gravity. On the other hand, if I were to throw it down, giving it a downward force to begin with, then the initial velocity might be something like 15 feet per second. And now we've got velocity, height, and gravity all affecting where it is. So this is the position function. You've used it before in Algebra 1 and Algebra 2. And it really just describes the position of an object falling under the force of gravity. All right, so now let's look at the first derivative of this function. So the h prime of t equals, now remember, 16 is obviously just a number, so is the velocity. If I throw something at 15 feet per second, 15 is just a number, and so is the height. It might be at 46 feet. Okay, so we're going to treat those like numbers in our polynomial, or like the coefficients of our polynomial and the constant. So if I take the derivative, I have negative 16 times 2, right, differentiating this first term, t to the first power. Okay, done with that one. Now the second term plus whatever this initial value is, the initial velocity. If I differentiate t, it goes away, so I just end up with initial velocity plus, well, this is just a number, and so we know that the derivative of a number is just 0. And so the h prime of t then is negative 32 t plus whatever the initial velocity is. And this is called the velocity function. And it tells you how fast the object is going whenever it is at some elapsed time. So not where it is, but how fast it's moving at that time. I can do this one more time and get the h double prime of t, which just means the second derivative, 2 dashes here. Another way to write this would be the d2 over d2t in this case. That would be a second derivative notation, not a notation I really like. Or I could say the y prime if I were using that notation. So it's just a notation difference. But the second derivative, doing the same thing, noticing that negative 32t, the derivative of that is just negative 32. And velocity is just a number, so it becomes 0. And so in this case, the second derivative is negative 32. And this is the acceleration function. And this tells you how much an object is speeding up at any given time. So if I were to wait 2 seconds and see what's the change in velocity or the acceleration, like putting your foot on the gas pedal, negative 32 is my answer. And the reason I get a constant for that is that gravity is a constant, right? Gravity pulls at a constant force. The object is getting faster and faster and faster, but gravity is a constant force of negative 32 feet per second per second. And it's negative because the object is falling, it's moving toward the Earth. And since it's moving toward the source of gravity, we call it negative. If I were to push something against the source of gravity by throwing it, then it would be a positive initial velocity, and I would never have a positive gravity because gravity always pulls toward the Earth, but that's why it's negative. Also, it's useful to notice or to know that sometimes I'm not working in feet per second, sometimes I'm working in meters per second. Different units lead to a different function, but only as the force of gravity. So in this case, the h double prime of t would be 9.8 meters per second, or per second squared. And newtons is another force. There are different constants for gravity depending on which units you're working in.